Now, it remains for us to show that s of x is equal to the right-hand side of the Selberg's asymptotic formula, namely 2x times log of x plus big O of x. So now let's prove this. Before we start the proof, let me recall theorem 422, which we proved in the section Selberg summation formula. The proof that s of x is equal to 2x log of x plus big of x is tricky. It is tricky from the beginning. We will start with the subtraction s of x minus gamma squared, where this gamma is this Euler's constant from theorem 422. Now let's plug in the definition for s of x. What about this gamma squared? We will first write this as, and here, this double sum is actually equal to 1, because the divisor sum of mu of d for d divides n is equal to 1 if n is equal to 1 and 0 otherwise. And this is due to theorem 263. Now we combine these two. And we perform a change of variable for this double sum. We change this to, and for those who don't see this immediately, let me provide some explanations. To explain that this double sum is same as this double sum, you simply have to notice that there's a 1-1 correspondence between set of the pairs d, n with d divides n and n less than or equal to x. And the set of pairs d, k with d less than or equal to x and k less than or equal to x divided by d. And this is a 1-1 correspondence given by, if you have a d, n on the left hand side, you map it to d, n divided by d. And if you have a d, k on the right hand side, you map it back to d, k times d. And you will see that these two maps are inverses to each other, establishing a 1-1 correspondence between these two sets. And now, let's continue. You may observe that this k is a vacuous variable in this summation, meaning it is just counting how many terms are there in this inner sum. How many terms? They are precisely the floor of x divided by d many terms. So we can simplify this to a single sum. And now we do our usual trick of removing the floor outside of x divided by d. We'll write this guy as x divided by d floor minus x divided by d plus x divided by d. I will split this into two parts. And as before, call this the error term. I will first bound this error term. By majorization, we see that the absolute value of the individual summand is bounded by, first this part is bounded by 1, and mu of d is also bounded by 1. And this difference is bounded by the sum of them. So we get the sum, which is equal to big of x. Why is this guy equal to big of x? This is by the theorem 423 in the section an important sum. In that section, we show that this sum is a big of x. Back then, this 2 could be any positive number. And for the other part, the summation of gamma squared for d less equal to x is simply another big O of x. So this error is bounded by big O of x. Now, it remains to study the first part. We will show that this guy is 2x log of x plus big O of x. Or, equivalently, if you divide both sides by x. So now let's prove this. We'll start by simplifying the left-hand side. And now let's look at this factor. By Euler's theorem, or theorem 422, we see this guy can be replaced by the harmonic sum 1 over k for k less than or equal to x divided by d plus the remainder term big O of d divided by x, namely the reciprocal of this. And we'll simply copy down the rest. And again, we're going to separate this sum into two parts. One part is this, plus the other part will turn out to be our error term. And again, we denote this by E. Let us first bound this E. What we do is that for the individual summand, mu of d is bounded by 1. And this difference is bounded by its sum, namely log of x divided by d plus gamma. And we will keep big O of d divided by x. Now, this 1 over d cancels with the d here. And when you sum up this part, for d less equal to x, what do you get? Again, by using theorem 423, you get big O of x. This is from the section an important sum. And eventually you get big O of 1. So this E is bounded by a constant. And now let's study the first term. Let us simplify this. The first thing we do is that we're going to merge these two iterated sums. We'll merge them into the summation for all d times k less equal to x. And we will combine this mu of d divided by d and 1 over k. And next, we're going to do a change of variable. Let n equal to d times k. You will see we can again break this sum into a iterated one. If the audience wants a more rigorous explanation, you can again establish the 1-1 correspondence between this sum and this sum. There's a 1-1 correspondence between the pair d, k and d, n here. And now let's continue. Let us pull this 1 over n outside of this inner sum and simplify this a bit. What we do is that we will rewrite this as log of x minus log of d. And we will group log of x minus gamma together. And the second part is the divisor sum of mu of d times log of d. Now, this guy, by theorem 298, is equal to, here I have to make sure to include this negative sign. Together with the negative sign, this is equal to lambda of n. So now let's take the summation. You see this part is the sum of lambda of n divided by n for n less than equal to x. Which, by theorem 424, is equal to log of x plus big of 1. Now what about the first part? If you look at this sum, this inner sum, you will see this is a perfect setting under the theorem 263. By 263, this divisor sum is equal to 1 if n is equal to 1 and equal to 0 if n is bigger than 1. So the sum will simply become log of x minus gamma, because only the term when n is equal to 1 will survive. So in the end, the whole thing will be simplified to twice of log of x plus a big O of 1. Since this gamma is a constant, so we merge this into big O of 1. And this, we will plug this back to here. You will see it becomes 2 times x times log of x plus big O of x. And together with this, we obtain that s of x minus gamma squared is equal to 2x log of x plus big O of x. But gamma squared here is a constant, which means we have verified this. And this finishes the proof of the second part, that s of x is equal to the right-hand side of the Selberg's asymptotic formula. And we are done with the proof of the Selberg's asymptotic formula.